Again, good morning for those who are here and those who are going to be watching this one later. Uh, good whatever time of the day it is. Anyway, the topic today is going to be on thermodynamics. We of course have quite an assignment at the end of this topic. So for those who are not live with us, you really need to watch the video also. You need to watch the recording, I should say, so that you can get your assignment done in time. And so we can, do you guys have any questions for me before we start in here? No? Okay, so we can get started with this topic today, which is thermodynamics, really, or the study of heat. Let me find where my notes are supposed to be. So we're doing chapter 6, and it's all about basically heat and temperature and thermodynamics in general. So I would basically, we're going to go through the topic itself. The science or the branch of science that is called thermodynamics is really a it's not only applied in physical science only, but it's also applied actually in biology too. So it has a very broad applications in terms of physics, in terms of chemistry, in terms of geology, in terms of astronomy, and in terms also of biology. So it's really, it has implications almost everywhere. At some point, I'm going to share with you a link, or at least a resource that I would like you to go guys and read about it, and it goes even to theology or the existence of God or not the existence of God and things like that. So basically, it has a lot of basically applications in real life, and it's a very important topic. This is the branch of science that was actually invented, if you wish, or it was discovered by an engineer. Usually, typically, scientists who start the process, and then later on, applied scientists come in and basically change the theory into applications, and then from there, engineers come in and actually make stuff out of these things. So usually, the role of the engineers is toward the end when it comes to the process of the applications and taking something from pure science to technology. But in this case, in the case of thermodynamics, actually it was started by an engineer, a French engineer by the name of Sadi Carnot, and he was working for in the French army at that time in the railroad, and he asked a simple question. That was in the 1820s, 1824, I believe. He asked a simple question: what is the most efficient engine? That was his question. In doing so, he invented what is now known as the second law of thermodynamics. So basically, he came up with the second law of thermodynamics, but he didn't call it the second law. He basically said, grant me this law, and he answered the question in a sense. He came up with the most efficient engine. Then people realized that there is something coming new in here into the mix. So what they did, they said, okay, before this law, because before we put this law, we really need another law before it. So the second law was what is now known as the second law, the one that Mr. Carnot worked with, was pushed further and became the second law, and the one that should come before it was called the first law of thermodynamics. We're going to discover this too in this topic. That was in the 1840s, around 1846 or 47 or something like that. Around that time, a little later, people realized, oops, we made a mistake. Really, before we talk about the first law of thermodynamics, which should have happened before the second law of thermodynamics, which was discovered first, and the first law was discovered second. Actually, we needed the third law. And the third law needs to come before everything else. So that's how the zeroth law came into play. So because they did not want to displace everything, so they kept the second law, which was discovered first, and named the second law of, which is basically the basis of which Mr. Carnot answered the question. And then the law that was supposed to come before it, which was discovered later, was called the first law. And then the third law, which really should be before everything else, was called the zeroth law. So that's basically how thermodynamics came into being a new science. So it was discovered backward, starting with the last law and going back until we came back to the most fundamental law. So that's how the story of thermodynamics basically came to be. And it's one of the most important branches of science. And it has applications, as I said before, everywhere, almost in every single thing that you can think of. Thermodynamics is at the heart of it. As a matter of fact, it is probably the foundation upon which the universe itself and the Big Bang happened. So it's really at that point, if we have a full understanding of it, that's really the... So just to emphasize the fact that this is a big deal, you really have to have an understanding of it. You will be given an assignment today, and you will answer it, hopefully. You're going to basically do some research based on what you have at home, and tell me about some of the things that have to do with heat and things like that. So we're going to talk about that the minute we get into there. And you're going to put it in the comments, and of course you can upload pictures if you can. If you don't want to upload pictures or you don't have access to a camera, that's fine, as long as you research the topic and answer the question for us. Okay, so in this chapter, chapter 6, we're going to talk about temperature. And temperature is really where the zeroth law is, okay? That's where we really need something to measure temperature. Remember what I said before, and it's still true, okay? If you cannot measure it, it is not physics. It's not chemistry, actually. It's maybe something else, but it is not part of the physical sciences, the one that we describe. So we really have to find a way of measuring temperature. If you take a cup of hot coffee, for example, you feel it's hot compared to, for example, another cup of water that you take from the refrigerator. So there is that feel to it. And if you can take another cup of something else, and you might say, oh, this is actually hotter than the cold water from the refrigerator, but cooler than the hot water, hot coffee. But that's still not quantized. There is no number appended to it. There is no number attached to it. So we really needed a number for that. And that's where the thermometer comes into play. And the thermometer really relies on the so-called zeroth law of thermodynamics, okay? And that is a concept of equilibrium, thermal equilibrium. So we're going to talk about the temperature. And first of all, we're going to talk in terms of intuitive fashion, basically, what we feel ourselves as hot and cold. And then, of course, we're going to come up with something that is more tangible to measure it, which is a thermometer. And then we're going to talk about a concept which is kind of important, and that is the absolute zero temperature, which is the temperature that nothing can basically reach, but it's the temperature that is nothing can go beyond that temperature, below that temperature, I should say. Then we're going to talk about the concept of heat and how to quantify it also, because that's one of the things that puzzled people when they were studying the branch of heat before the onset of thermodynamics, and that is, they call it the calorific fluid. Because if you take, for example, a hot cup of coffee, for example, and put it next to a cold cup of, doesn't matter, coffee or water, for example, and you connect the two. And if you put your hand around the connection, you will feel something is going, something is moving, going from the hot to the cold, okay? So people believed, actually, that there was some sort of a fluid, not in the sense of a liquid, not in the sense of some sort of a water or a coffee, but there is a heat fluid that is flowing from place to place. It puzzled people. They didn't know what that was. It took the genius of another scientist, Mr. Joule, actually, to show that actually heat is energy. And there is an experiment he conducted that heat, the one that you feel on your body when you're hot, or the cold, which is the lack of heat, if you want to call it, is actually to energy, that's all, okay? And he was able to give us a number appended to heat, how much that correspondence between what we thought was a calorific fluid or calories and the energy that we know including kinetic energy, so that gave us a way of converting heat into energy and vice versa, which is a very important thing. That's why now you have engines everywhere. You can do convergence between electrical energy, mechanical energy, and heat, and vice versa because of that experiment. We're going to explore the laws of thermodynamics. In this book, they introduced the third law of thermodynamics, which is really not popular. It has really not much applications, honestly. So the main laws are the three laws, namely the zeroth law, which allows us to invent the thermometer. Then the first law of thermodynamics, which gave us this equivalence between energy and heat, namely that heat is a form of energy and the total energy of a system is conserved. And that's what the first law is. And then the third law, which states basically that no way you can have a spontaneous process for heat moving from a cold source to a hot source naturally. If you have a pump that pumps heat from the cold source to the hot source, like what we have in our homes, for example, we have AC units. The room is actually colder, the house is actually colder than the outside, but it takes more of the heat from the inside and dump it to the outside. So that's an AC unit. If you have an AC unit, it can reverse the process. It takes heat from the cold and put it outside in the hot. And that's actually why the refrigerator also works too. You have food, for example, sitting at, let's say, for example, temperature of 50 degrees Fahrenheit. You put it in the refrigerator, it takes more heat from it and dump it outside where it's actually hotter and lower its temperature to 40 degrees or 35 degrees, depending on how much temperature you want to have in that refrigerator. And as a matter of fact, if you don't trust me, just go behind your refrigerator and feel it. It feels hot because it's taking heat from the inside of it, putting it outside. This is unlike, for example, a heater which works backwards. So a heater and a refrigerator are actually reverse processes. So again, the second law of thermodynamics talks about spontaneous process, not a process that is, for example, aided with an external agent. So if you take, for example, a hot cup and a cold cup, and you put them next to one another, heat will always flow from the hot to the cold. It doesn't go from the cold to the hot and make the cold colder and the hot hotter. It's always going to take the hotter, make it cold, and make the colder and make it hot, basically, brings them to some sort of equilibrium. And the process is actually far more reaching, the second law of thermodynamics. If you take the system, including the one that has an engine in it that pumps energy out of the cold and puts it in the hot like a refrigerator, if you take that system, namely the refrigerator, the inside of the refrigerator and outside of the refrigerator, you will find that actually the whole process obeys the second law, no matter what, okay? And a concept that generates from there is the so-called concept of entropy. The entropy of the universe always increases, okay? There is no way that it can decrease. And we'll talk about that concept of entropy, and you probably hear about it in the literature a lot. And that's why you really have to have a full grasp of it. It doesn't matter which field you're going to. It's a good idea to understand it. It's related to order and disorder, but it's also related to this second law of thermodynamics itself. And it's the one where debates are and books are written and philosophers are spending a lot of their times talking and basically a lot of debate on that topic. So I hope that by the end of this today, you will have an understanding of what that is. You talk about black hole, for example, we're going to talk about them. And black holes, we can understand basically they have supermasses, and that supermass becomes too much to overcome the force of repulsion due to the electric charges, and then it even overcome the nuclear forces and collapse everything to a singularity. Well, that's fine, but there is a problem. People were thinking, okay, what happened to the information? What happened to the entropy of the system? Is it going to really go away? So again, my point in here about the entropy is a very big topic. It influences everything that we can think of. So we have to really hopefully have an insight into what that means. By the end of the day, that's really the heart of this thing in terms of a lot of things, which is really the second law of thermodynamics. That's a question that Mr. Carnot actually asked. Mr. Carnot, C-A-R-N-O-T. Okay, that's how Sadi Carnot. He's really the one who started really this whole branches of, I mean, there are other people who were working on heat before him, and there are other people working on other things, but he's the one who put it together and tried to ask a simple question. He was not interested in anything else, honestly, other than making a more efficient engine than probably the engine that runs the trains at that time in Europe, in France. Okay, so that was something. Then we're going to talk about specific heat. Specific heat is a key concept that we're going to explore in this. It has a lot of applications. It has implications on the weather, climate. It has implications on a lot of things. I mean, applications on a day-to-day business. We'll talk about thermal expansion, which is also critical. For example, we use it in different thermostats and different applications in terms of thermal expansion, and we have to be very careful as engineers when we build, for example, things that have metals in them, because metals, they expand. Actually, all materials do expand with heat and contract with cold. So we have to really talk about that, and then we'll talk about the water, which has a unique property among everything else that we know. Everything that we know, if you lower its temperature, its density increases because all of its molecules start to come together. So its density increases because it becomes denser, becomes closer to one another. The volume shrinks. Well, water has this peculiar behavior. When you make it colder, at some point it's going to contrast around 4 degrees Kelvin, around 4 degrees Celsius. It's actually going to expand again. You're lowering its temperature, it's going to expand again. When it's ice, it's actually less dense than it's water. That's why ice floats, okay? And that's why the Titanic sank, because if the ice was inside the ocean, the Titanic would have continued that way, straight through. Actually, it's more important than that. It's if it was the other way around, if the water behaved like everything else, the oceans would freeze from the bottom up, and that's bad. Because that means marine life will be basically will be devastated by that, and Earth will ultimately cool to a temperature that is going to be zero, because everything starts to cool, and over time the buildup of the coldness, so it's going to have everything basically colder. So that's really not good. So the fact that water has this peculiar property really what enabled the existence of marine life, which ultimately led to basically life as we know it on the surface and the entire planet being the way it is. So basically, that's some of the things that we're going to be talking about. This is the entire chapter in a nutshell. I hope you guys have had read through it and discovered that there is a mistake, which is going to be part of your assignment too, to correct that mistake, because there was a mistake in one of the slides. Anybody found the mistake, or you didn't have a chance to go through it? No?
I didn't have a chance to go through it yet.
Okay, very good. Thank you. Okay, there was a mistake. We're going to find it. It's somewhere in one of the slides. We're going to go through it, and that's going to be part of your assignment to fix that mistake. Okay? So, temperature. Again, we have it's initially, like I said, and here this is basically what you yourself will feel. I mean, you can feel it without having to have anything about it. Oh, this is cold, this is hot. Something in between. Actually, this is colder than the first one, but it's hotter than the second one. So it's you can start comparing things. But if you do it this way, like I said, it's really not a good way of there is no number appended to it. So it's still not science. It's still not physics. Okay. So we needed a measurement. We need a number to be attached to it. So the zeroth law, which is not stated in here in this book, and I'm going to tell you exactly what it is it talks about thermal equilibrium. Okay. Take, for example, a hot cup of water. Okay. Take it from super hot. and put it next to, in the air, for example, in your room, okay? And come back to it after, doesn't matter, after an hour, for example, would you find it the same heat or would the temperature come down to it? What do you guys think?
It'd be cold.
It becomes colder. And how cold is it going to be? Colder than the room temperature or hotter than the room temperature or the same room temperature as that of the room where you are?
It would.
Same as room temperature.
Yes,
Same
it
room
reaches what is known as thermal equilibrium with the room. Okay, so you have two media in this case: the air in the room and the cup of coffee that you brought, and you forgot, and it was sitting on the table, and you went and did everything else. You went shopping. You came back. Now the cup of water or the cup of coffee has the same temperature of where the room is. So we say in this case they reach a thermal equilibrium. Okay. Same thing. If you take, for example, a cup of water and put a lot of ice in it, want it to be cold so that you can drink it, you put it on the table, and then you go shopping, come back an hour, 2 hours, 3 hours later, it doesn't matter. You're going to have found it that the same thing. It's just reached the same temperature of the room. You guys understand that? Yes? Cold or hot, it doesn't matter. Yes or no?
Yes. Or
Okay, here is the question that I want to ask you now. Let's do this experiment, okay? And you can try it. Take a cup of hot coffee and put it on the table, okay? Super hot. Put it on the table. Take another cup of water that has ice in it, a lot of ice in it, and put it next to it in the, they don't have to be in contact. As long as they're in contact, they're in the same room. Put it on the table. Go and do whatever you want to do. Come back after hours. What do you think the temperature, or how does the cup of coffee would feel versus the cup of water that's
About the same.
both of them would feel the same thing.
mm,
Okay, remember that the cup of coffee was in contact with the air, with the room, and the cup of water was in contact also with the room, but somehow both of them have reached their equilibrium together. They are mutually basically now in equilibrium. So this is what the zeroth law says, basically, and it's a mouthful a little bit, okay? That if I have system A, think of it of the cup of coffee, okay? And system B, which is in this case the air, okay? And they have reached their equilibrium. They're fine. Now they're the same temperature if you want to feel them. And you have system C, which you can think of it as a cup of cold water that you put ice in it. And the air, in this case, system B, okay? They are also in thermal equilibrium. What the zeroth law says that then A and C are also in thermal equilibrium. Okay, do you guys understand that? So if both these two, coffee and air, are in thermal equilibrium, then water, cold water and air also, and they are in thermal equilibrium, then in this case it goes by saying that coffee and water in this case have reached the same temperature. So this is what allows me to invent a thermometer, because all I need is replace the air in this case by something that I can gauge it with. Let's say, for example, take the temperature of water and call it, when it freezes, 0 degrees Celsius. When it's completely frozen, I'm going to call it 0 degrees Celsius. When it boils, I'm going to call it 100 Celsius. Anywhere between them, going to divide it. So as I'm raising the temperature of the water, I'm going to divide it in denominations of 1, 2, 3, 4, 5, 6, all the way to 100. Okay. Then I have gauged my thermometer versus water. If you don't like this unit, you say, okay, I want it when it freezes to be 32 degree Fahrenheit. When it boils, it's actually 212 degree Fahrenheit, okay? And I'm going to watch the temperature as it's rising between them and call it degree each time the temperature rises. So I have 180 denominations between 32 and 212. And now I have inverted the Fahrenheit scale. So I take that thermometer, now I put it in contact with something else, okay? Not necessarily water. and the thermometer will go up and down depending on what the temperature of the medium that I have it in contact with. And now with confidence, I can append that number to the temperature of that material because I have already gauged my thermometer versus water. So basically, this is what allows me to invent the thermometer. This is what allows me to actually come up with the concept of temperature. Now I have a number associated to it, whether I'm using the degree Celsius or whether I'm using the degree Fahrenheit, or we will later on learn about it in terms of Kelvin. Okay.
That's so cool.
Okay.
I think
So
that's
this
really
is
cool.
yeah. So this is the zeroth law, and this is the explanation for it. So this is what allows me to invent the thermometer, if you wish. Okay. Okay, so the concept of temperature, again, there is a sad story in here, okay? Mr. Boltzmann, I think there are two N's in his name. I'm not sure, I think there are. Of course, beforehand, people were trying to understand what in the world is temperature, okay? Because you can feel it, but what it is. So he came up and he said, you know what, the air that you have in your room in here is made up of tiny particles. He assumed that they are made of tiny particles. He didn't see them. He didn't really do any experiment with them. And he calculated their kinetic energy. He calculated their momentum based on their size. And he did a calculation using Newton's laws of motion as they hit the wall or hit your skin. And he calculated and found what looks like laws that people have found from previous chapter, PV equal to nRT basically. And he explained it that way that it works. People made fun of him, and they were teasing him, including some scientists too. Hey, because we can see these particles that he's talking about. Now we know. I mean, now we have advanced so much behind this time that we know that actually they are called molecules. Okay, that's what makes up all the particles. But of course, he was ahead of his time, and people were teasing him, and they okay, I grabbed some of your particles, Mr. Boltzmann. Can you have them? And he committed suicide. So that's basically the sad part of it. But his theory really talks about these particles as they move. And depending on their motion, the motion has what is called a degree of freedom. There is a translation. These particles can move, for example, a molecule, for example, of this room is made up of N2, which is nitrogen, and oxygen, O2. So this N2, for example, the two atoms of nitrogen that form the molecule of nitrogen, they can move this way or that way, up and down, in and out, or left and right, okay? So this is called translation. The center of mass is moving back and forth. So this is called translational motion. So that's one way for it to move, okay? Another way for it to move is by spinning around its axis. This is true usually for gases, okay? Gases do this behavior a lot because they are free. They are not really, the distance between different molecules is big so that they do that. Now, for the liquids, usually they're closer from one another and they cannot really move without bumping into one another. So what they do in this case, they rotate, they spin around their axis. So for example, the molecule of N2 can spin this way, or can spin this way, or can spin actually this way, okay? So there is also 3 ways for it to spin. So in this case, that is rotational motion, okay? Or in the case of solids, it's even closer. They cannot even do that. So what happened in this case, they can vibrate. And for the case of the 2 molecules, for example, for the 2 atom molecules, like for example, N2, they're called diatomic molecules. In this case, they can only vibrate along one direction, okay? But in other, for example, when you have H2O, for example, which has 3 atoms, they can vibrate along between the oxygen and the hydrogen atom, or they can actually, the atom itself can vibrate this way. So there is different ways for it for vibrations if you have more than a diatomic atom, polyatomic atom in this case, molecules, I'm sorry, then in this case, they have a different behavior. So that is vibrational. So all of this is ways for it to move, okay? And that is how Mr. Boltzmann actually, you can compensate for that and actually explain what temperature is. So temperature has to do with the kinetic energy, and kinetic energy is the energy of motion, In the 1D motion, in the translation motion, it's 1/2 of mass times velocity squared. But in rotation, it's actually expressed in a different fashion, okay? It's expressed with something called the moment of inertia and angular velocity. So there is other expressions for it. In this case, it's expressed actually in terms of the spring, basically what is equivalent to a spring, okay? But the point being in here is the temperature has to do with the kinetic energy. It is the kinetic energy. The faster the atoms, the molecules move, the hotter the room is. The colder the room is, the less motion you have in the molecules, okay? So if they move slower and slower, at that point you have less and less temperature. So that's basically how this is related to. So when you are lowering the temperature, there is less motion of the molecules or the particles of the medium that you have in whether talking about vibration or rotation or translation, okay? Doesn't matter which, or the combination of two or more of them, okay? So there is less kinetic energy. So this is typically for liquids, and this is typically for solids, okay? So they all have temperature, all of them. Whether a spoon you put it, for example, on the oven, it's made out of iron, but at the end, you're gonna feel it. You're gonna feel the heat coming to your hand. So again, we talk about the thermometer, and the thermometer is coming from the zeroth law, and it's measured by the expansion of the liquid for in that case. For example, in the case of mercury or alcohol, again, we're going to take that mercury and see how much it expands. So we're going to talk about the thermal expansion a little later. And for each degree that I'm going to raise the temperature of the water, put it under a furnace, for example, raise the temperature, and watch the thermometer rise in temperature, and you can actually scale it accordingly, okay, versus that of the water, okay? So that's basically how we're going to define thermometer. And from there, we have a thermometer now. It doesn't matter which, we have thermometer. We can measure temperatures, okay? We use, in the rest of the world, 100 degrees Celsius as being basically the temperature of boiling for water. And this is what you see in the scale in here for the, what is it called? The centigrade, okay? Or we use in the United States in here the Fahrenheit, and there is a one-to-one correspondence between the two. I mean, there is a formula that is basically gives us one of them. Actually, you can look at this scale in here. 60 degrees Celsius is about 140 degree Kelvin. I mean, oh, Kelvin, I'm sorry, Fahrenheit. For example, when the weatherman is talking about a temperature that is comfortable around 70 degrees, for me, for people who were raised somewhere else, it's confusing because 70 degrees is very close from boiling temperature. So you really have to do the conversion to find that actually this is room temperature. This is comfortable temperature. So you need to do the conversion. So this is the scale, and this is a thermometer. This is what allows you to measure temperature. And it's all granted based on the zeroth law. Oh man, it's not writing. What happened? What happened to my pen? It's lost. Never mind. Okay, I got it back. Zeroth law. Okay. Okay. Again, the kinetic theory is actually the one that Mr. Boltzmann actually invented for the gases, and how he explained the temperature itself, okay? And the thermal energy is the one that is related to the energy of the heat, or the energy of temperature, I should say. There is a word that you really have to be careful with, regardless of what field you're going to be in, okay? And that is temperature, and heat. They are not the same thing. They are not equal to one another, okay? Temperature is a measure of how fast the particles of the material are moving, because it reflects the kinetic energy, that's all. But it is not the kinetic energy per se. It just measures how fast they move. Okay? Heat, on the other hand, is an energy. This is in joule. This is what we know energy as we measure energy in typical fashion. So you have to be careful with these two concepts in here. Heat and energy are, heat and temperature are not the same. Okay? In other words, a cup of coffee, for example, may have more heat in it than I'm trying to think of an analogy in here. Okay, let me take two examples. Okay, you have a cup of coffee or a cup of water, for example, that is half filled. Okay, and you have a cup of water that is fully filled. Okay, cup filled to the brim and a cup halfway. Both of them have the same temperature when they're at equilibrium with the medium. Both of them have the same temperature. You can put the thermometer in both and they have the same temperature. But the one that has twice as much liquid will have more heat in it, more energy in it than the one that is actually has half cup. So there is more in one than the other. So heat and temperature are not the same. The fact that both of them have the same temperature or one of them has more temperature than the other does not necessarily mean the one with more temperature has more energy in it, more heat in it than the other one. So it can extract, actually you cannot say it has heat at all. You can say how much heat you can extract from it or dump in it. Heat is a value that has to do with interaction, that's all. Doesn't exist per se in an object, okay? It is not what is known in physics as a state variable. It is not. Temperature is a measure of the state of the object. So you can always measure temperature now. But a cup of water, you can extract more heat from it or less heat from it, depending on how much basically you're going to have it with another one. So I'm trying to make a little bit in here distinction between the two so that you guys are not confused between the two. One of them is a measure of something and the other one is a measure of something else. And one of them is actually a property. Temperature is, and the other one is not a property of the object. Okay. Question 1. So this is not one of the questions you're going to be submitting today. There is twice as much molecular kinetic energy in 2 liters of boiling water as is in 1 liter of boiling water. Which will be the same for both? Now, you have twice as much molecular kinetic energy in a 2 liter. I just gave the example. For example, you have a half cup and you have a full cup. Both of them, the 2 cup has twice as much kinetic energy and it's twice the same amount, twice amount. The other one has half and it's half. So the correct answer is the temperature, because both of them, they could be sitting in room temperature and both of them would be at equilibrium. So both of them have the same temperature in here, okay? That's the correct answer to it. Because you doubled the mass, you doubled the content of the liquid, but you doubled its energy too. But the other one, it's still half, and it has the same amount, half the energy, so both of them have the same energy, the same temperature, I'm sorry, okay? Here is the absolute zero, and again, this is resulted from experiments. People were playing with the low density gases, not playing, really experimenting. And they noticed the following behavior. If I lower the temperature, this is the temperature, this is 0 Kelvin, 0 Celsius, I'm sorry, people at that time, they were using Celsius. So if I take a gas with a certain density, for example, and lower its temperature at some point, this is the curve, how it looks like in terms of the, for example, the pressure. Okay, it doesn't matter what I'm looking at. The pressure of the gas, okay, the volume of the gas. Okay, I do the same thing, pressure or volume, it doesn't matter. Both of them will behave the same fashion. If I take another gas, this is how it's going to look like. Another one looks like this, and another one has probably this behavior. They're not the same slope though, they're not tilted the same way. But all of these lines, they meet somewhere and they meet in the same place. Okay, they meet at the same point. And that means that that is where they meet. At that point, the pressure drops to 0. That is how the zero temperature, the absolute zero temperature was basically found. And that temperature where everything stops is negative 273 Celsius, okay? At that point, You cannot go below because the pressure will be negative. It doesn't mean, I mean, it's nonsense. Or the volume shrinks to zero. There is no volume of the gas if you can maintain the same pressure. So that doesn't mean what happens in here. You lost all of your gas? No, you still have gas, but its volume shrinks to almost zero at that point. Of course, you don't do it experimentally. You cannot reach that temperature. That's another thing with it. You can come close from it, but you cannot reach it, okay? And so at that point, that's basically how you can think of it. That's where the temperature, where everything has a limit below it. So that's why now the Kelvin was invented. The Kelvin, which is another measurement of temperature, which starts from here, from zero all the way. So room temperature, I mean, when the water freezes, it's actually not 0 degrees Celsius, but now it's 273 Kelvin, okay? Room temperature is going to be about 300 Kelvin. So that's how the Kelvin was invented. That's how the temperature Kelvin was invented. And that's a measure of temperature. And another warning in here, people, when they talk in temperature in Fahrenheit, they append to it the 0 in here to say degree Fahrenheit. When they talk about temperature, for example, in Celsius, they append to it also the 0 on top of it to say it's a degree Celsius. But when they talk about Kelvin, you put it as a unit. So it's a temperature Kelvin. Okay, so when you're with K, okay? So that's the Kelvin, and that is the 0K basically. And the K here stands for Kelvin. Okay. So again, this is what I was talking about. The volume starts to shrink. I mean, we're putting it 0, but that's a theoretical value. Practically, you cannot reach that volume of 0. Therefore, you cannot reach the temperature of 273 Kelvin. Practically, there is no way. Actually, as a matter of fact, the universe right now, on average, its temperature is 2.73 Kelvin. That is the temperature of the universe, on average. I mean, somebody might tell me, oh, wait a minute, the sun is about what, 5,000 something Kelvin? 5,500 Kelvin? It's super hot compared to the Earth. The Earth right now, it's on average about 300 Kelvin. Yes, and actually inside the sun, for example, it's several million, probably 20 million Kelvin. Inside, I mean, on the surface of other stars, for example, what is that one? Sirius star. It's probably about 25,000 Kelvin on the surface itself, let alone inside. So those things are super hot. It's true, I agree. But on average, the entire universe taken from end to end, including the interstellar space, the space between the stars, it's about only 2.73 Kelvin. So it's cooled so much from the point when it started in the Big Bang up to this point. Can we reach 0 Kelvin? Theoretically, maybe, okay? And I say maybe because actually even theoretically it's not possible, because there is a new theory that at that point fluctuations due to quantum mechanics starts to take place, and even there you cannot reach it. So practically it's impossible. Okay, so you cannot tell me, okay, I started with this many liters of gas, for example, 2 liters of gas, and start to shrink, lower the temperature. At some point, the volume starts to shrink, lower the temperature, the volume shrinks, lower the temperature, the volume shrinks, lower it to 273, I should lose my gas. Doesn't mean it doesn't, you cannot. So that's why it's a theoretical limit, not a practical one, okay? But you can reach 0.01 Kelvin. There is no problem with that. So you can reach it. And actually, experimentally, people have reached very low temperatures. Okay. But you cannot reach 0 itself. Okay. So again, thermal energy, it has to do with the energy of basically that is released, for example, in this case, in the form of sparks, which is no more than a plasma, which is basically the transition of the particles as they move from energy level to another energy level. Okay, the concept of heat, again, is defined as flow of thermal energy due to temperature difference. The key word in here is flow. Heat is a transition between two different energy levels, okay? an object that has this much temperature has this much energy, kinetic energy, this much thermal energy, if you wish, okay? Another one that has lower temperature has this much thermal energy, which has to do with how much kinetic energy at the end, how much inside energy it is. That's what we're talking about when we say energy in this case in here. It has to do with the temperature. The higher temperature you have, the more energy that you're supposed to have. The lower temperature, the less temperature. But now, if you extract or dump heat into that, that means you're going to take some of that thermal energy and put it somewhere else. And the process with which this goes, transitions from point to point, that is what thermal energy is. That is, I'm sorry, what heat is. So you take, for example, a hot source in here, hot, and you have a cold source in here, C, and heat will flow then from the core, provided that there is contact between the two. That is what we call heat. The symbol for heat in when we do problems is Q. So this is heat. Q stands for quantity of, I think, quantity chaleur in the old days also. So they use Q for quantity of heat, okay? So this is the symbol for heat. That is basically, it's the process, it's a flow, okay? And as I said before, people used to think that it's some sort of a liquid, some sort of a calorific fluid, actually, that's what they called it, okay? Again, we talked about this one. 1 liter of 1 liter of water in left, 3 liters in right, both absorb the same quantity of heat. Okay, so if you dump the same quantity of heat, put them in the same furnace or 2 equivalent furnaces and let them stay for the same amount of time, 15 minutes, for example. One of them has a third amount of water than the other one, well, the temperature of the less water will increase 3 times versus the one that is 3 times bigger, okay? So if this temperature, for example, rises by 15 degrees Celsius from whatever it was, this will rise only by 5 degrees Celsius because you have 3 times as much quantities in here of that one. Provided you put them on the same heat source or equivalent same heat sources, same furnaces, put a smaller quantity in another one, and look at the thermometer, okay? Look at the temperature and how much it rises. So whatever it was from before, they were both in thermal equilibrium. They had the same temperature. One of them will rise only by 5 degrees Celsius. The other one will rise by 15 degrees Celsius. When the same amount of heat is added to each of the 2 containers, the temperature increases in which? So when the same amount of heat is added, the temperature increases. Depends on the amount of water. If this one has more water, that's the temperature will increase less, okay? Heat is energy in transit, okay? That is a key thing in here. So that's why it's not temperature. Temperature is actually, you can measure it with thermometer and find out exactly what it is. Heat, you have to wait for it to interact with somebody else, okay? So that's the big difference between them. The unit for temperature, for heat, people were puzzled with that. Of course, they gave it a unit. They said, okay, take 1 gram of water, okay, sitting at 14.5 degrees Celsius. At that time, they have already invented the thermometer, and put it under a furnace and watch for the temperature to rise from 14.5 to 15.5 degrees Celsius. 1 degree only. What you added in here is what we call a calorie. You added a calorific fluid that is 1 unit. That's what they called it, okay? That's how the definition was. Of course, they didn't know what that was, but they gave it a definition because it was obvious there is a process in here. So they said, okay, take 1 gram of water, okay, 1 gram. If you can do 1 gram and you can do 10 grams or 100 grams or 1 kilogram of water, do 1 kilogram of water, divide by 1,000 at the end of the day. That doesn't matter. That's not a problem. So take 1 gram of water, sitting at 14.5 degrees Celsius, put it under a heat source, like a furnace, wait for it to raise from 14.5, look at the thermometer, until it reaches 15.5 degrees Celsius, you have 1 calorie at that point. You added 1 calorie to your system. Of course, you have to pay attention to the word calorie in here and pay attention to the letter C itself. That's going to be part of your assignment. Is it capital or lowercase? In this case, it's lowercase. That is the definition of the calorie. Now, Mr. Joule did an experiment, actually. He took a container of liquid, of water, and he attached the string around a mass that is going through a pulley, and the pulley is actually attached to a stir in the water. So when the mass falls, the stir will turn, and that agitates the water, and he put a thermometer there. And he noticed that there is, as the mass falls, it converts, it has a potential energy which he can measure in joules, mgh. It fell in the height h, 1 meter, for example. He knows how much mass it has fell. He can find g, which is 9.8 from the experiment of Mr. Galileo, and he found how many joules actually went in. Now he has a thermometer inside the liquid, and he can see how much temperature rises. And he was able to tell you that, look, 1 calorie is the same as 4.19 of this energy. People called it joules later on in his honor, okay? So now that is why heat and energy are the same. It's because of Mr. Joule's experiment, okay? Otherwise, before this experiment, it was a puzzle. We know how to measure it, we know how to quantify it, but we didn't know what it was. Now we know. Heat is energy. That is due to Mr. Joule's experiment. And the unit was named after him in his honor. So the calorie and the joule are one and similar to one another, okay? Which brings me to another problem in here that we deal with on a daily basis, which is the calories of the intake that we take in our food, the food that we eat. It's made out of calories. That's basically what you see. You go to any kind of restaurant and they should list the number of calories in anything that you buy. You go to the grocery stores and they list it. How do they know? Take, for example, a hamburger, burn it, and put it on a container, put the water on top of it, and see how much temperature of the water rises. That's very simple, okay? If you don't know how to do that, take a piece of bread of the burner of the hamburger and measure that. Take whatever content it is, the meat, and measure that, and burn it and see how much heat you release from that. That is how much calories you have in there. And the numbers were in the thousands. So instead of scaring people and tell them you have 70,000 calories, they said, no, you have only 70 capital C calories. So when you see capital C, it's already 1,000 times calories, okay? The lower C. So that is why the capital C, I was telling you earlier, you have to pay close attention to it when you're reading your food, okay? How much there is an intake in it. Is it capital C or lowercase c? They cannot put lowercase c because there is no such a thing. Where you eat a hamburger, for example, you're going to get 420 lower calories. That is not possible, or 720. That is not possible. It has to be in the capital C, okay? Which brings me to this point in here again. 1 food calorie equals 1,000 calories. You have to have that conversion in mind all the time. That it is not 4.19 joules, it's actually 4,190 joules. So this tiny thing in here has this much energy in it, okay? And that is your assignment today, okay? I took these pictures actually this morning, okay, from my refrigerator. I grabbed these things from the refrigerator. Look at the calories for, what is this one in here? Okay, I grabbed it, I didn't mean to. The milk, okay? It's 100, this is a whole, what is it? A whole milk, okay? 170 calories in it, capital C. So they are honest enough to tell you that this is the same milk, but it's from almond milk, okay? 40 calories. This is from vegan spread, 80 calories. And look at the trick in here of this guys, okay? Best foods, which is mayonnaise. They put the whole word in capitals, okay? But they're actually, it's a capital C. I mean, if they really were honest enough to put it, I'm not saying that they're not, so I'm not trying to blame anybody in here. Please don't go and start writing letters to them and tell them you're cheaters or anything like that. But the point being in here is they have the right to do that because they are not in violation of any rules. I mean, they're capital C, capital C. Yeah, put the whole thing in caps, that's fine. But it's 90 calories. Okay, here is your assignment for the day today. You're going to look around your house, your kitchen, okay, and find, first of all, one or two items, okay? Look at the label and find how many calories in there it has. And then you're going to tell me whether or not it's properly spelled, okay? The way it's supposed to be is the first letter has to be capital C. If you find them writing it lower C, that is where you have to be alarmed. There's something wrong in there, okay? You have to really be skeptical, and not only highly skeptical, and actually that's where probably you need to write a letter, okay, to the vendor. So it has to be capital C. Worst case scenario, probably it's, did you find it? Yes, Josh. This is for the discussion afterwards, okay? So this is what you're going to be doing. You're going to find one, at least one, hopefully two items in your household. We're going to find the number of calories, properly spelled or not, and what's your reaction? For example, it's been a long time for me where I gave up completely milk and I'm doing almond milk. So because I find it less calories in it, and actually I am lactose intolerant, so I don't do that anyway. So that's another thing in there. And you see the spread between one or the other, and here in this case, there is not much difference, but at least one of them has doesn't have milk in it and eggs, and the other one does. So that's some of the things that you could have in the discussion, okay? And that should make you aware next time when you go to the groceries, and whether or not you really are in care or don't care, whichever your opinion is, about this issue at all. But at least this is part of your assignment for the discussion. I would want you also to react to other people's input in there. Were you surprised to see this many calories or this less calories, as a matter of fact, in something that you like or you don't like, okay? It doesn't have to be in your household. I mean, you could go wherever. I mean, I don't know if they label the pizza and all of the other things, but you'll be surprised, okay, how much of these things are in there. You guys understand the assignment for the day? I'm going to put the instructions more in the discussion things in here today, okay?
I do. I have a question.
Yes.
So we need to find one or two items, and all we have to do is write down how many calories are in these two items.
As it's properly spelled too, because you have to tell me. I mean, the way it's spelled, we need to know about it, because if they put lower C, you have to be very critical of it. And then I want your reaction to it, whether or not you're surprised or not, or what is that going to tell you, or can you find a better alternative to that if you don't like it, or is this the best alternative that you already have? Yes?
Got it. Thanks.
Okay.
Do you want a picture of it, or you just want us to type it in?
If you want a picture, that would be nice, okay? You don't have to have a picture, but I basically took pictures with my cell phone and basically made a new slide and put them in there. Yes, so this is your first assignment for the day today.
And the proper spelling has to have an uppercase C, right?
It has to have an uppercase, unless somebody is playing a game, like, not really, I'm not trying to say playing a game, unless somebody found a work around it and put the whole thing in caps. If you find it lowercase c, I need to know about it. Everybody needs to know about it. If they put lowercase c, we don't care about the rest of the letters, honestly. I mean, if it's a big, like the best foods in here, for their real mayonnaise, they put the whole caps key C, but they put it everywhere. Actually, it's not just that. For this entire thing in here, 1 tablespoon serving. And that's another thing also, you need to find out exactly what the serving is, because that's a key. I mean, you could have less calories if they tell you have this many, okay? So you have to pay attention to how much food in there, okay? 1 table, that means that now, if I want to, and I like mayonnaise sometimes, I put very little in it because of the taste, that's all, okay? So that's something that is part of the reaction. So maybe you like it so much and you don't have any health issues to be concerned of, but now you're mindful of the fact that it's too much, so maybe you just take a little of it. Okay? I'm going to put the instructions more in the discussion afterwards. Yes?
Sounds
Yep.
good.
Okay, very good. So let's move to the next question, which is also the other problem that you are going to fix today, and that is the discussion that is part of your second assignment. The quantity of heat needed to raise the temperature of certain substance, a specific amount, is 1 capital C calorie, okay? So this is the same amount of energy. Initially, when I posted it, it says both of this. That's not correct. It's only this is correct. Okay. 4.19 joules actually is just 1 calorie. So that to be specific. So that's 1 lowercase calorie. 4,190 joules is actually 1 capital C calorie. See that this is the difference in here? So the correct answer in this one is actually A. So I need you to fix that. That is part of your second assignment. So you're going to tell me question related to 1 big calorie in the food is actually fixed, and it should be only 1 calorie and 1,000 lowercase calories. Okay? Got it? That's the second assignment for the day. If you look at your slides from the ones that are on Canvas, you will see that the correct answer by mistake was put 4.19. So you have to fix that. Oh, I'm sorry. It's really both of this, okay, which is not correct. Okay. Everybody got it?
Not really.
Okay. The question was, you have 1 big calorie, how many is that? And it gives you several options. It gives you 1,000 little calories, or 4.19 joules, or both, or none. The answer, if you look at the notes, it says both. That is incorrect. The correct answer should be only 1,000 little calories. So in your answer sheet in there after the discussion, you're going to tell me that you have fixed this problem, that you know that 1 big calorie is actually equal to only 1,000 calories, okay? Here is the answer to it. Is 1,000 calories. Cherry? Yes?
Yes.
Got it.
Okay. Okay, so let's continue this. And so the next discussions are talking about the, in here you have, for example, what is it? The question that you have half cup of tea needs rises by 8 degrees Celsius. If you, for some reason, you double the quantity of full cup of it, how much is going to go only by half, which is the correct answer is 4 degrees Celsius. Okay, so all of these discussions are basically related to this idea, which brings me to the first law of thermodynamics. And when heat flows from one system to the other, it gains or loses heat. So that means the energy of the system is, in this case, conserved. The energy, overall energy is conserved. So that's basically what the first law is. Okay. This is another thing, if you have time, depending on your religious convictions, and hopefully this will not shake your faith in religion if you already have it. If you don't have it, then you don't have a problem. Is a book by Isaac Asimov on the so-called Last Question. It's a very short book, and that was one of the favorite stories that everywhere he went, people asked him to tell it. And it's a fun story, okay? So if you have had a chance, go through it. And it has to do with the second law of thermodynamics, which basically, like I said, states that no fluid, no heat flows spontaneously from a cold source to a hot source, okay? So in his story, people basically ask him to tell it, and it's a fun story, okay? Now, if you have strong religions, convictions, and you think that this is maybe not something you don't want to do, this is up to you. This is not an assignment. Yes? Because it will shake your faith in God himself, okay? So you don't want to do that. But if you don't have that, it's fine. Okay. If you're doing it for the sake of research, do it. Okay. So the author is, I don't know if you guys are, I mean, he's got a lot of sci-fi stories, including The Foundations and all of that, is Isaac Asimov. He was a chemist, okay? So, and this is the so-called third law of thermodynamics. This is the one that has no system can reach absolute zero temperature. Again, we said that experimentally it's not possible. And this is now stated as a law. People don't really use it much because it doesn't have practical applications, honestly. Okay. I'm gonna skip around because I noticed that the time is running out. And I trust that you guys, this is the concept of entropy, and I mentioned earlier this is a very important concept, and it is related to the second law, actually. And entropy is a measure of how orderly or disorderly an object is, okay? You can relate, actually, the spontaneity or the lack of spontaneity of heat flow from a cold source to a hot source to the way the energy is distributed inside the system. The more opportunities for it has, the more, in this case, the system spreads around, and that's basically what's going on in here. Take, for example, what is it? For example, a gas sitting on one side and separated with a shield, and the other side is empty. When you remove the separation, the gas will spread around completely. This is actually another way of saying the same second law, because now gas found a new room for it, so it's going to spread. This does not violate the first law in terms of conservation of energy. It could go back to one side, but we don't see that. For example, if you see this object, for example, I'm trying to think of it. An egg, for example, okay? You take an egg and you drop it, or a cup and you drop it, okay? When it drops, it breaks into so many pieces. That is disorderly. Now it's more disorder than when it was in one piece. They are all next to one another. This does not violate the law if all of the pieces come together and basically become the cup again. So why does not happen? Because of the second law, the entropy, okay? That is basically what it is. So if you go to YouTube, for example, right now and watch a cup, all of a sudden that was broken and come back together, you know that's fake. It's not gonna work. But in terms of physical laws, it does not really, in terms of conservation of energy, at least, it does not violate that. So why does not happen? Again, because of the second law of thermodynamics, and that is the entropy at work for you. So if your mother complains about your room, that it is disorderly, you have your defense. Tell her it's the second law of thermodynamics. The entropy increases. So that is the natural thing of things. Don't complain about that, okay? That's your defense, at least against that. Okay? Now, the thing with it is, if you let any system by itself, is going to evolve into that state. It's going, I mean, if you have a house, for example, that is not cleaned all the time and maintained, we're basically trying to prevent the second law from taking its effect. If you let it by itself, dust will pile up, things start to break, and the whole thing goes into disarray. Again, that is the entropy of at work. So again, like I said, the entropy is a very, very wide topic. It has implications in physics, chemistry, why chemical reaction is possible and another way it's not possible. Again, you do the entropy, you calculate the entropy, you calculate the enthalpy, which is another concept in here, and you measure the entropy and you find that the reaction will happen in this way, only this way, possible. It can happen this way in other possibilities if you add energy to it. Hence the concept of and exothermic reactions, one that release energy and one that extract energy, and the possibility for it to happen or not is governed by the second law. It governs everything, not just chemistry, which is biology also, covers everything in the universe itself. The actual evolution of the universe itself is linked to it. As a matter of fact, the concept of time and the flow of time is actually related to the concept of entropy and the second law of thermodynamics. They're intricately related to one another. Why time always flows into the future and not in the past. And if you take Newton's laws or any physical laws, they work both in the past and in the future, but only the time seems to be flowing in one direction and one direction only. That is because of the entropy. That means that the way that we say it actually in terms of entropy is that the entropy always increases, okay, of the universe. Can never go back and start to shrink again. This is what actually Mr. Boltzmann has discovered, actually, the restatement of the second law in terms of the entropy. And now when physicists and scientists go actually to Vienna, they skip all of the fun stuff in Vienna in terms of coffee. You know how Vienna is known for that, and all of the stuff that has to do with the museums and theaters and all of the other things, but they go straight to his tomb and reflect one more time on, actually this law is inscribed on his tomb actually, to reflect on that and what he did for us, and how he was badly treated by his peers when he came up with this genius things. Okay, again, this is in terms of the second law in terms of entropy. Natural systems tend to disperse from concentrated and organized energy states toward diffuse and disorganized states. Basically, that the entropy increases. Okay. The total amount of the entropy in any system tends to increase with time, becomes more disorderly. It's the same thing as Mr. Sadi Carnot's basically postulate. That is exactly equivalent, that heat does not flow from a cold source to a hot source. Spontaneously, that is. I mean, don't tell me about the AC and the refrigerator. That is aided. As a matter of fact, if you take the AC and the refrigerator as a system with the outside environment included, namely with the kitchen itself included, the entropy still increases in that case. Okay? So yes, the things inside the refrigerator are getting less and less entropy in them. They're getting more organized. But overall, if you account for the kitchen, it's still true. The second law still holds. Okay? And that's what it talks about, the overall system. Your garage measure issue, in this case, the entropy of the universe is increasing. Okay? That is the second law. Okay? So that's when my wife complains about the room, I tell her, forget it, okay? Go to your room. It's the second law of thermodynamics. Okay, specific heat is another concept in here, and that is the amount of heat taken by an object, and this is specific to every single element, okay? Depends on the mass, and it's intrinsic, okay? So the amount of heat, again, is Q, and is proportional to the amount of mass, and it's proportional also to the amount of temperature. For example, if you raise the temperature of water from let's say 10 degrees Celsius to, let's say, 20 degrees Celsius, in this case, the difference is 10, okay? That's why it's a good idea to use Celsius for most of the time, is because it's the difference in Celsius is the same difference in Kelvin, which is what we really need in when we do problems. So this is the difference in temperature times the mass times the quantity. In this here case, it's specific to everything. So water, specific heat of water, which is by definition 1. And then you can relate other materials to it, okay? Water has a very high specific heat, and that's why it's used as a regulator for the climate. That's why when you live near the oceans, it's more regulated climate than when you are inland, because of the fact that land has has lower specific heat. That means its temperature will rise faster by its little amount of heat versus the water. Water retains more of its heat, okay, than, for example, a piece of iron. And you can do that. For example, take a spoon inside boiling water, and both of them, of course, they boil. It's very hot. But when you remove the spoon, it's colder than when the still hot liquid, which is the soup. So you have to wait for it a long time before it cools down. So water has a very high specific heat. It retains a lot of its heat. It takes a lot of energy to raise its temperature too, versus, for example, metals. So substances have their own specific heat capacities. So it depends on, so in this case, why it's super hot, it's because of the liquid water that forms the main part of the pie in this case. Okay, we talked about this one in general. we're going to talk about this one when we talk about geology more down the road, okay, and the weather and things like that. This is what I was talking about in here, which has a higher specific heat, water or land. In this case, it's clearly water. So it takes a lot of heat to raise the temperature of water versus that of the land for the same amount of mass, of course, okay, comparative masses. Which brings us to a thermal expansion, which is the last topic in here. We still have a few minutes to can cover it. So again, metals in general, materials in general, they expand due to heat, okay? And this is where you see the buckling of the roads, and that's what prompts engineers, for example, when you're driving on the freeway, you see sometimes like a continuous separation between the different slabs of the freeway. Because during heat they come closer, and when they expand and they come closer, and during cold weather they actually separate a little bit. So you need gaps in them, otherwise this happens. Okay. And also the same thing is with the power lines, for example. Also, you see them; they usually give them a lag, so that in the winter they shrink and they go higher. In the summer they come down a little. Otherwise, they will basically contract enough to break. And that's an experiment we usually do in classroom, but we cannot do now because of the fact that we don't have access to it. And this is one of the applications for this one in here. And that is basically you can use the two metals with two different properties, coefficients of expansions, and that will give you, if you wish, if one of them is expanding, you can gauge them actually to see how much temperature. So you can use them actually as thermometers too. Or you can use them, for example, as thermostats. There is a link in here that I'm going to post to you guys and discussion. Oops, let me go back. I'm sorry. That I would like you to go to it. I know it's probably, no, you don't have it, I think. Let me give you in the discussion session so that you can go and watch Mr. Hewitt himself explain to you this concept, okay? The author of the book. Okay, I think that was the last point in here in this chapter, no? Yeah. No, the water expansion, I'm sorry, the water expansion is actually, like I said, it's a peculiar property that allows the survival, basically, and the expansion of life on Earth. And it has this property that when it's liquid, the molecules are moving around, but when it organizes itself, all of a sudden, the distance between the different molecules is greater, okay? So now, that's really why the volume expands, and like I said and before, that's what caused those two guys from the movie to die, the two actors to die. Okay, so again, this is the property of the water. It has a higher density when around 4 degrees Celsius, and at that time it did not freeze yet. So frozen water, which is ice, has a lower density, which means it's going to float. Okay. So that's why our oceans, they don't actually freeze from the bottom, or ponds, they don't freeze from the bottom up, they freeze from the top down, which allows the survival of marine life, which basically the basis of all life on Earth. Okay, that's where it started everything. Any questions for me for this chapter? Other than the fact I'm going to give you specific instructions on the prompt. On one of the prompts, there are two of them today. On one of them is to fix the mistake on that slide, where you're supposed to fix the 1 calorie, capital C being 1,000 calories. And the second assignment has to do with what you have to pound at home. You guys don't have any questions? I'll see you next week.
I just want to make sure I understand that. So instead of 3 questions like we normally have, we have just the 1 question we have to fix and the assignment.
2.
Okay, just those 2?
Just 2, yeah. Sometimes
Okay.
you will have 1, sometimes you will have 2, sometimes you'll have 3. So today you only have 2. Okay?
Mm-hmm.
Okay.
Thank you.
Okay, thank you
Thanks.
guys. See you guys next week. Be safe.